Hi guys. This is the notes for section 5.3, which deals with graphing radical functions. So what we're going to do is look at this first example where it says graph the following function. What are the domain and range of the function? Is the function increasing or decreasing? And then at the bottom, we're going to find the max and min for the interval from 0 to 12. All right, so our first step is to make a table and graph. Okay. First thing is we have the square root function. This tells us that we can only have a positive x value. Right. So we'll start off with 0. Okay. And let's just figure out our y values after plugging in some x values. Okay, so 0, if we plug it into this equation, we're going to get 0 for y. All right, now let's try 3. If you do that, right, we get square root of 3 times 3, which is square root of 9, which gives us a y of 3. If we try 12, right, 12 times 3 is 36, and then the square root of 36 gives us a solution of 6 for y. And then the last would be 27. 27 times 3 gives us 81. So the square root of 81 gives us a output of 9 for y. All right. So we can graph these 4 points. 0, 0 is here. 3, 3 is going to be 3 and about there. All right. Doesn't have to be perfect. 12, 6, and then 27, 9. All right. And that is an example of the graph for square root of 3x. Now our domain is the set of x values. Well, we can see, right, it starts at 0, and then it keeps going all the way to the right. So our domain, right, would be our x values, and it's anything greater than or equal to 0. Right? We can't have a negative solution, right, because we have a square root function. So it's anything greater than 0. And then our range, right, is our y values. So our y values, we can notice, right, it starts at 0, and then it keeps going up, and it's going to keep going on. So same thing, y is greater than or equal to 0. It's our range, right, because as x increases, y increases. And then to tell increasing or decreasing, right, that tells us we find that by looking at the slope of it. As you can see, the slope of this line is always staying positive, right, up and to the right. So if the slope is always staying positive, the function is increasing. Okay. And then the last piece, what is the max and min? We're looking at the interval from 0 to 12. Okay. So our lowest point, or our min, right, this is our y value, right, is the max and min, is the y value, and these are the x values you're looking at. Okay, so the minimum would be y equals 0, right, And the max, right, is the highest on the interval from 0 to 12. Well, the highest is right here, which is at 12.6. All right, so our y equals 6. All right, so that's one example. Why don't we go on to the next one, part B, which deals with a cubic function. So we see this example, it's the cube root of 2x. Okay, we can have negative values in the cube root, right? Our parent function ends up looking like this. Okay, so we're going to get a picture something like that. All right, so you can pick really any values. Usually a good one to start with is 0, right? And if we plug in 0 for x, we're going to get 2 times 0, and the cube root of 0 is 0. Okay. I'm going to pick 0, 4, -4, 13.5, and -13.5. And the reason is because these numbers give me a perfect cubic number in here when multiplied by 2. And then when you take the cube root, you get a whole number for your y solutions. But you could pick any number, really. You'll just get decimals if for your y values if they're not perfect cubes. But right, if we plug in 4, right, we get 4 times 2 is 8. So the cube root of 8 is 2, because 2 times 2 times 2 gives us 8. And then the cube root of -4 times 2, so -4 times 2 is -8. We can take the cube root of a negative number, right? It's because -2 times -2 times -2 gives us -8. So our solution is -2, right? Because the cube root of -8 is -2. Then we have 13.5 right here, right? 13.5 times 2 gives us 27, and the cube root of 27 is 3, because 3 times 3 times 3 gives us 27. And same negative, right? Negative 13.5 times 2 is -27, and the cube root is -3. So I just put out values that I knew I could take the cube root of. Now I'm going to graph. So 0, 0. We also have 4, 2. Just be careful, right? This graph goes by 2s, and this one goes by 2s, but it looks a little bigger. Right. -4, 2. And again, our graph looks something like this. And like this. All right, so our domain, right, is the set of x values. Right, as we can see, x values go left and go right, and they have an arrow, so they're going to infinity. So it's all real numbers, right? Because you could like 12s on it, 100, -100, all real numbers. The range, right, is the y values. As you can see, it's going up forever and it's going down forever. So again, it's all real numbers. All right, any y value is going to be on there. We got to tell whether it's increasing or decreasing. Well, I know the arrow is pointing left, but if you look at the slope of this line, right, I'll put it in a different color. It's still going up and to the right this whole time, whether it's small slope or large slope, it's still going up and to the right. Therefore, this function is also increasing the whole time. Right? Even if you look here to here, right, it's still going up and to the right, the slope from those points. So any points, 2 points on here, right, the slope is going up and to the right, therefore it's increasing. Now we're looking at the max and min from -4 to 4, right? The minimum would be right here, and the max would be right here, okay? Again, these are the y values from -4 to 4. So the interval is the x values, the max and min are the y values. So our max is the highest point there, which you see is y equals 2, and the min is the lowest, so y equals -2. So I have 2 more functions for you guys to try. Again, I gave you large tables. You necessarily only need like 2 points for the square root function and 3 points for our function here, right? Our cubic function. Our cubic function should look something like this, and our square root function looks something like this. Okay, so I'm going to have you pause this and try these two, and then I'm going to show you the solution in a second. All right, so here's the solutions. As you can see, in part A, right, if you plug in 5, right, you get square root of 0 is 0, so that's why it's at 5, 0 right here. Then I just tested another point that I knew I could take the square root of, so I tested 9 for x, because 9 minus 5 gives you 4, and you can take the square root of 4, which is 2. And then I did 14, because 14 minus 5 is square root of 9, which is 3. Okay, so I just picked nice numbers. And then we'll find out in a little bit that we can actually graph these just using certain transformations. B, right? I tried -1 because I wanted to find something in here to get 0. Right, so -1 gives you cube root of 0, so 0. I did -9 because -9 plus 1 is -8, and the cube root of -8 is -2. And I also picked 7 because 7 plus 1 is 8, and the cube root of 8 is 2. And again, you only need 3 points, right? You need the point here that kind of changes the curve, and then you need 2 point to the right of the curve and the left of the curve. All right, so now we're going to kind of write the radical function and then name the certain parts so that we can do transformations to it. Okay, so it's pretty similar to regular functions, right? We have a on the outside, but now we have a square, a root sign, right? A radical. And then we have a number n here. When we have the square root, the n is just implied that it's 2. But you know, with the cubic root, n is like 3, 4, 5. It can be anything, right? And that's what we call the radicand. Then we have x minus h plus k. So those letters should remind you of a couple things. So, right, our a represents our vertical stretch or compression, right? So if it's greater than 1, it's a stretch. If it's between 0 and 1, then it's a compression, right? That'd be like a fraction of like 1/4 would be a compression, where like a equals 2 would be a stretch. H is our horizontal translation, so left or right, and remember it's minus h here, so you go the opposite direction of what you see. And then k, right, is our vertical translation, so it goes up or down, right? And again, n is called our radicand, and right, if it's 3, it'd be like the cube root. If it's just not there, then it's implied it's square root. All right, so let's look at an example of rewriting this radical function to identify its transformations. All right, so first thing you want to do is figure out the parent graph. Well, we can see this is a cube root function, so the parent graph would just be the cube root of x. All right. So our first step in doing this, right? So step 1 is what we want to do is find out what you can take the cube root of in each term. Okay, so we look at the terms, right? So cube root of each term. Okay, so take 64x and 192. Well, 64, right, is a perfect cube root. We can take the cube root of 64 because 4 times 4 times 4 gives us 64. So I'm going to rewrite 64 as 4 cubed, right? Because I'm going to take the cube root of it and take it out of that radical. X, right? We can't take the cube root of it because it's just an x. So it's just going to stay as x. And then 192, we can split this up, right? 64 times 3 gives us 192. So I rewrote 64 as 4 cubed like I did for 64x. And then we're also missing times 3 because 4 cubed is 64 times 3 gives us back this 192. The reason why I wrote it like this is because I'm going to take the cube root of both this 4 and this 4. Well, technically those 64s, and then the 4 is going to come out of the radical. Okay, so, right, I'm going to rewrite this radical. This function. So f of x equals the cube root. Instead of writing 64x, I'm going to write 4 cubed times x minus, and then instead of 192, I'm going to write 4 cubed times 3. That's because I want to take the cube root of this and this, right? We want to take out from each term something that we can take the cube root of. So when I do that, I'm going to change it to g of x because it's a new function, right? We took out a 4, and then we have the cube root of x, right? Because this cancels out and this cancels out, minus 3 left over. All right. Now that we did that and rewrote this, we can figure out what transformations happen to this original parent graph. All right. We can see there's a 4 on the outside now. So that means we have a vertical stretch of a equals 4, right? Because that's our factor is a, right? And we have a 4 outside. Now this minus 3, right? We go in the opposite direction. So it'd be to the right 3. Right? And that's a horizontal translation. Right? And that comes from our h, right? Because our h is 3. And then we don't have a k. We don't have a vertical translation in this part. All right. So now we're going to use transformations to map the graph of a given function. Okay. So we're given it in the a times the radical of x minus h plus k. So we can just identify the transformations, and then this is our parent graph right here, this f. So we're just going to move the parent graph given the translations. Okay, so right, this plus 5 tells us up 5. This plus 3 tells us left 3. Remember, it's the opposite for h. And then this 2 tells us stretch a equals 2. All right. So the first thing we can do is change this first point 0, 0 by going up 5 and left 3. Okay. And then we could also, so let's first do that, right? So we'll up 1, 2, 3, 4, 5, right? And then left 3 would be right here. So our starting point would be -3, 5 instead of 0, 0. Okay. Now, right, the other points change because we have a stretch of 2, right? So for the stretch of 2, right, what we'll do is we'll take the next point, right? We'll actually make a table. All right, so x, y. Right, so we knew -3, 5 is our starting point, right? We can test something else. I'm going to test 1, okay? And if we plug in 1 into this equation right here, right, we get 2 times the square root of 1 plus 3 plus 5. So you get 2 times the square root of 4 plus 5. So you get 2 times 2, which is 4, plus 5, which is 9. So we have 1, 9. So I'm going to plot that point. So here's my -3, 5, and then 1 here, and 9 here. And then I'm going to make my curve, and there is my graph. All right, so here's another type of example. So this says, how can you rewrite the following radical function to identify its transformations? These ones are like example 2. All right, so we just have to do a couple extra things. So let's go through these. So what I'm going to do for square root of 9x is I'm going to teach you another technique. So I'm going to separate the 9 and the x. Okay, so I just rewrote it as square root of 9 and square root of x. And the reason I do this is because now we can easily take the square root of 9, and we have our solution of 3 square root of x. And right, our original parent function is just square root of x. So the only transformation we have is a stretch of a equals 3. All right, that's a vertical stretch. All right. Now let's do b. All right, I'm going to first factor out a 4 from this 4x plus 16. So square root of 4, I factored out a 4. So I just have x, and then plus 16 divided by 4 is 4. So I just factored out this 4, right, plus 7. Now I'm going to separate them like I did in A. I'm going to separate it as square root of 4 and square root of x plus 4. And then plus 7. So I get 2 times the square root of x plus 4 plus 7. Now, right, we know 2 is a vertical stretch of a equals 2. This tells us left 4, and this tells us up 7. So again, those were more examples pretty similar to example 2. Now, this is our last type of example. We want to find the radical function that's represented in this graph. Okay, so what we need to do is figure out, looking at this point right here, that should always be at 0, 0 for the parent function, right? And we know this function here is a cubic function, so this f of x should be cube root of x, right? Now, as you can see, this is our g of x, right? The one we're trying to find. And this point 0, 0 has not moved. So if it hasn't moved, then we don't have a vertical stretch and we don't have a horizontal stretch. So our h is equal to 0 and our k equals 0, right? Because there's no vertical or horizontal stretch. Now, sorry, vertical or horizontal shift. There is a stretch though, right? We can see that this function is kind of higher than our normal f of x function. So what we can do is first graph our f of x function or our parent function. All right, so our parent function for the cubic, okay, so f of x, I'm just representing f of x as my parent function. All right, we know 0.00 is on it. We also know we should get 1, 1 because the cube root of 1 is 1. And then we also know the cube root of 8 should be 2. All right, so 1, 1 should be on. Oh, sorry. They go by 2s, so be careful. So 1, 1 should be on it. And I keep messing up. All right, that's 1, 1. All right, and then 8, 2. So 8, 2 should be right here. So this is our parent function, right? And we know it also goes the opposite way, right? So if we have -1, we get -1. And then if we have -8, it's -2, right? So -1, -1 is here, and then -8, -2 is here. So there's our parent function. Right, so we can see there's been a vertical stretch. As you can see, g of x is higher. Right, so we just need to compare our g of x function to our f of x function to see what our vertical stretch is. Right, so I'm going to make a chart again. Right, we said 0, 0 stays the same, so we can't tell by 0, 0. Our next point, though, we have 1, and then we have 2. Right, and then we also have 8 and 4. So what we want to do is look at our y values, right? So we want to find out what our original f of x y values were multiplied by to get these g of x y values. Well, obviously you can see 1 times this 1 right here times 2 gives me 2. And this 2 times 2 gives me 4. So that means we are stretch of a equals 2 because, right, and then we can see the other ones if we kept going, right, -1 should be at -2, which it is because -1 times 2 is -2, and -8 should be at -4, which it is on that g of x function. So this is our stretch. And then our last step is to rewrite it using our formula, right? We know it's a times n root of x minus h plus k. So the only thing we have is a because our h is 0 and our k is 0. So we're just going to rewrite this as 2, and then it's the cube root. So our n is 3 of x. And here's our solution. So now for this one, I want you to try it. And then I'll show you the solution. So pause this, try this on your own, and then I'll show you the solution in a little bit. Just to remind you, right? First, do your parent function, right? It starts at 0, 0. Okay. And then it should be 4, 2. And then it should be 9, 3. Okay, because we know our parent function, f of x, is the square root of x. Okay, so you need to figure out what g of x is right here. Remember, first find out how much over you've gone and how much down you've gone from the starting point. Okay, that'll give you your h and your k, and then you just got to check using a table whether or not you have a vertical stretch or not. All right, so now here's the solution. We've gone, this point went left 5, right? And then it also went down 4. Okay, so left 5 means our h is 5, and down 4 is our k is 4. Sorry, this should be -5, not just 5. Right, and then we don't have a stretch here, so the only thing we'd plug in is our h and our k. Right, our h was -5, so instead of x minus h, it becomes x plus 5, and then we have -4 because it's down 4. So both of those should be negative for our h and our k. And that's it.